Hi, this is Coach Heichel. I'm bringing you a basic podcast over Unit 9 gases. So let's start with notes on pressure worksheet. On the notes on pressure worksheet, it says that pressure is simply defined as a force per unit area. So think about pressurizing propane. Okay, when you pressurize a gas enough, it's eventually going to turn into a liquid. Well, there's some conversions that we need to know. And on this sheet, it tells us what we need to know about it. So it says that one atmosphere is equal to 760 millimeters of mercury, or 760 torr, or 1.01 times 10 to the 5th kilopascals, which just is 101.325 kilopascals, or it's also equal to 14.7 psis. So when you're just going to convert the following units of pressure, it's really, really easy. So let's take this, okay, and we know that that number is the same as writing 0.357 because you just moved the decimal place over to the left one place because that's what the negative stands for. Well, let's put our unit. We know we have atmospheres, okay? So we have atmospheres, and in the chart above it says that for every 1 atmosphere, we get 760 torr. Now, I'd teach my kids to do it like this because if you have an atmosphere here and you have an atmosphere here, they just cancel out. You get rid of that unit, you multiply it going across, so 0.357 times 760, and you're going to get your answer. Does that make sense? Great. Let's move on. I'm going to do number 3 just because it's one of the easier ones for me to do. So we got 989 torr. Okay, well, since we have torr at the top, what's going to go on the bottom? That's right, torr is going to go on the bottom. So we got 760 torr is 1 atmosphere. And we get that from the conversions at the top. Now, since this one's on the bottom, you take 989 and you divide it by 760. Does everything make sense? The rest of them are going to work the same way. Just do them like this and you'll never get them wrong. So let's go down to notes on temperature. Okay, we know temperature is the average kinetic energy of particles within a sample. So think about gases, how they move around. Okay, as those gas particles bump into each other, they create friction. Friction is just temperature. So the kinetic energy is the movement. The friction is what you get as a byproduct of that movement. Now, there is one typo on this sheet that we didn't catch in time. We apologize for that. So let's mark off this 9 over 5, and it should actually be 5 over 9. Okay, and if you're better with decimals, the 9/5 is going to equal 1.8, and 5 over 9 is going to equal 0.55. Some people like decimals, some people like fractions. You can use either or to give you the right answer. It doesn't matter. Okay, so our first one, we're trying to convert 100 degrees Celsius to Fahrenheit. Okay, well, Fahrenheit equals, we're going to use this formula right here. Fahrenheit equals 1.8 times the Celsius temperature. That's what the degree C means. So 1.8 times 100 plus 32, which should give you 212 degrees Fahrenheit. That one's pretty simple, right? Okay, let's move on to a Celsius to Kelvin. Well, Celsius to Kelvin, we're going to degrees Kelvin, so K equals the temperature of the Celsius plus 273. So that's simply just saying 273 plus 37 degrees, or 310 degrees Kelvin. Okay, I'll do one more. I'm going to do one that requires 2 steps. So number 4 is 700 degrees Fahrenheit to degrees Kelvin. Well, we don't have a direct formula for Fahrenheit to Kelvin. So you got to take the Fahrenheit, you got to take it to Celsius, and then you got to take the Celsius to Kelvin. So it's a 2-step process. Well, we have a formula for degree C here that uses Fahrenheit. So let's do that. So let's do 0.55, which is the same thing as saying 5 over 9, times 700 minus 32, which is 668. Okay, so now we have degree C. Once we get that degree C, we simply add it 273 to it, do all that work, eventually you're going to get a fairly large number, and you should get 643, right around there. Sorry, I had to check my notes to make sure I had the right answer. You should get 643.47, I believe. Okay, temperature is kind of easy, just use these. You don't need to do any dimensional analysis, which was the method that we did on the previous example. Just follow the formulas. If you start with something, look for what you're going to use the formula that it states. Okay, so now we're going to move on to molar volume. We're going to skip all the notes because I'm going to fill you in on that as we go through it. So all right, so now into molar volume problems. Again, I'm just going to give you a few examples and then let you work them out on your own. So when we're looking at this, it says that 1 mole of gas, any gas, at standard temperature and pressure, which is what STP stands for, occupies 22.4 liters. So if you have 1 mole of hydrogen gas, it only weighs about 2 grams, but it's going to occupy 22.4 liters of space. Think about right about 11 2-liter soda bottles. That gas is going to occupy, if all the molecules are spread out as far as they can go, the kinetic energy is as low as it can possibly go, it's going to occupy 22.4 liters. So it wants to know how many moles of neon gas are going to be in 78.41 liters. Well, let's go back to the way we did the first example. Start with what you're giving. I always write that in the top left corner. 78.41 liters. Okay? Well, this conversion says that for every 1 mole, we're going to have 22.4 liters. Since we have liters here, our liters is going to have to go down here. So 1 mole is 22.4 liters. All you do is divide, and you should get 3.5. I always start with what you have in the top left corner. Divide by the unit to get them to cancel out. Okay? So now on to the next one. We want to know the volume. So when we're talking about volume in this unit, we're talking about liters or milliliters, something that's going to contain the gas. Well, we start with 0.8 moles of something. Okay, we're going to write that in the top left quadrant. And we know that for every 1 mole, we occupy 22.4 liters. Well, there's our volume. So we got moles on top. So we're going to put 1 mole on the bottom. We're going to put 22.4 liters on the top. Cancel out our moles. We're left with the volume of liters. Simply multiply 0.8 by 22.4, and you should get around 17 point, I think it's 92 or 29. So I'm going to put 92 just to be safe. Okay, and when we talk about moles of molecules, it's one more step, but it's a fairly easy step. So always start with what you have. So 39.1 liters. Okay, we got to get this liters to moles because we have a conversion from moles to molecules. Awesome. So let's start with 22.4 liters down here on the bottom. Since we have liters on the top, we want to get to cancel out in 1 mole. Okay, liters is done. Now we got to get moles to molecules. So we know that 1 mole equals 6.02 times 10 to the 23rd molecules. And that's of any stuff. It could be molecules, could be particles, could be atoms. So you just simply multiply 39.1 times 6.02 times 10 to the 23rd, and then divide it by 22.4. That's going to give you your correct answer. Okay? Okay, we're going to move on. Now, I know y'all were a little confused about when you got to the box. What do you do for the box? It's just a blank page. Well, something we did in class just to basically show our kids the way gases act. And I can do a brief description of it, and it'll help you carry throughout the entire unit. So I'm going to take a little bit of time, and please bear with me. It's going to be kind of hard to keep up with all these drawings, okay? So let's say we have 3 boxes, okay? We have 1 box. We have a 2nd box. And then let's do our blue for our 3rd box. Okay? Notes on the box. Alright, we're going to make our molecules black just because it's going to be easy to see. Let's say we have all these little gas molecules. Okay? All these gas molecules floating around in this specific volume. This red box represents one volume. Okay? Is the pressure going to be high or low? Okay, well, there's somewhat of a lot of particles and a small amount of volume. So the pressure is going to be relatively high. Now let's say we get rid of this red box. Okay? Let's say we get rid of it. So I don't have a function just to erase just this one box. So let's just imagine that this box is gone now. Okay? This is gone. So now all these molecules are now floating in this big black box out here. What just happened to the volume of it? That's right. The volume increased, so you can expect the pressure to do what? Since the volume increased, the gas molecules are spread further out, the pressure is also going to decrease. So we taught our kids that volume and pressure are inversely related. As you increase the volume of something, you decrease the pressure. You give the gas particles more room to expand out and be away from each other. Okay, and then you could do that again. Imagine you take this black box out and then you put all these here. Okay, well, you increase the volume even more, and then the pressure goes down even further. Okay, I hope that's just a little bit of an example. I know it's not very good because you didn't experience it in class like our kids did, but it's the best that I can give you. So now we're going to go into some actual gas laws. So we're going to start with Boyle's law. Boyle's law says that gas and volume varies inversely. Okay? The volume of a gas and its pressure varies inversely. Okay? When temperature is held constant. So the formula is P1 times V1 equals P2 times V2. Well, the way I always do it is P1 V1 equals P2 V2. And I'm only going to give you one or two examples of these because these are really easy. It's just basic algebra. You just got to know what to label what as what, and then you'll be fine. Read this problem. It says a sample of oxygen gas occupies a volume of 240 milliliters at 740 torr pressure. What volume will it occupy at 800 torr pressure? Okay, so we have 3 out of the 4 things that we need, so we're good. So this is our V1. It's volume. It's milliliters. Our pressure 1 is going to be its torr pressure, and then pressure 2 is going to be 800. So we're solving for V2, okay? Well, if you think back to algebra, V2 equals, if we want to get this V2 by itself, we have to do what? We got to divide both sides by P2, and then we get V2 all by itself. So V2 is going to equal 240 times 740, because that's our V1 and that's our P1. P1, V1. Then we divide that whole thing by our pressure 2 of 800. You divide all that out. Sorry, I'm checking my notes to make sure I tell you the right answer. Divide all that out, you should get 231.25. Okay? Okay, let's go into one more, and then I'll let you do the rest of these on your own. So, a sample of carbon dioxide occupies a volume of 3.5 liters. That's going to be our V1. A sample of carbon dioxide occupies a volume of 3.5 liters. So that's going to be our V1 at a pressure of that. That's going to be our P1. On these, it doesn't matter what form of pressure you use. If you use kilopascals, torrs, millimeters of mercury, as long as both of the units are the same, you're going to get the same answer. And it wants to know pressure if we decreased it to 2 liters. So if we're decreasing the volume, we can expect our pressure to go up because they're inversely related. So we're going to solve for P2. Well, P2, if we follow this formula, P1 V1 equals P2 V2. If we're going to solve for P2, we got to divide each side by what? By V2. So P1 V1, so 3.5 times 125. Then we're going to divide all that by 2. Multiply that out, and we get 218.75. So our pressure went up because we decreased the volume. So Charles' law says that the volume of a gas directly varies with its Kelvin temperature, assuming that pressure is constant. So you can't really determine whether it's going to go higher or lower because it varies directly. So sometimes it'll increase it, sometimes it'll decrease it. So let's do a few of these example problems. I like this form of the formula better because most people know how to cross multiply and divide. Okay, so V1 over T1 equals V2 over T2. That's going to be our formula for Charles' law. And it's important to note that every time you have a degrees Celsius on this, you've got to convert it to Kelvin by just adding 273 to that number. So that's our volume 1. This is going to be our temperature 1. This is going to be our temperature 2. So let's set it up the way the formula tells us. Let's put V1 over T1 and then V2 over T2, and let's see what we're missing, and then cross multiply and divide. So volume 1 is 250 milliliters over temperature 1 is 25 C, but we got to convert it to Kelvin. So we're going to add 273, which is going to give us 298 equals, well, we don't have our volume 2, so we're going to put an X there, over, we have 95 C. We got to convert that to K. We simply add 273. That gives us 368. So you work for that if you're solving for X. If you're not good at algebra, you would simply do 250 times 368, divide all that by 298. You do all that work, you're going to get 308.7. Okay, so simply cross multiply and divide on these. We'll do one more and then I'll leave the rest for you. So it says we have a gas at 40 degrees C, occupies a volume of 2.3 liters. What's the temperature? So we're looking for T2 when it's raised to 6.5 liters. So our first volume is 2.3. Our first temperature needs to be, what is that, 313? Because we added 273 to 40. We're going to change our volume to 6.5, so our V2, we're going to solve for T2. So you multiply 313 times 6.5, cross multiply. So we're multiplying this by that, we're going to divide it by that. Divide that by 2.3, do all that fancy spancy work, you get 884 degrees K. Awesome. Let's go on to the next gas law. So his formula states that P1 over T1 equals P2 over T2. Okay? So go through and read our question. Determine that a pressure change when constant volume, okay? So volume's not going to be a factor in here. Gas at 1 atmosphere is heated from this to that. Now let's go ahead and convert it to degrees Kelvin because it makes it easier. That's our standard temperature. So pressure 1 would be 1 over 20 plus 273 is 298. No, sorry, 293. And we're going to solve for X. We know that 273 plus 30 is 303. So you multiply all that out. You do 1 times 303. So 303 divided by 293 is going to give you just a slight increase. It's going to give you 1.03 ATM. So we didn't change the temperature a whole lot, so our pressure exerted on that gas isn't going to change a whole lot as well. So let's do the next one. We have 0.37 ATM at 50 degrees. Well, 273 plus 50 is going to give us 323 degrees K. And we're going to change it to standard temperature, which standard temperature is 273 degrees Kelvin. So cross multiply, you get 0.37 times 273. You're going to divide that whole thing by 323. Do all the math in your calculator, and you're going to get 0.313. So our temperature went down, so we're having less friction, so our pressure is also going to go down very slightly. The rest of them like that are the exact same way. Okay? So let's go on to the next one. We're going to go into what's called Avogadro's law. Now, Avogadro, remember, he was the guy that had to deal with moles, and he said that for every 1 mole of something, it's going to occupy 6.02 times 10 to the 23rd molecules, particles, atoms, whatever. It's just a number of representative particles that can be found in any 1 mole of any substance. So here's his formula. Just write it like this. V1 over N1 equals V2 over N2, where N means the number of moles. Okay? So V is the volume, N is the number of moles. So it's going to work the same way the last 3 or 4 have worked. You're going to cross multiply and divide. Read the question, fill out your V1s, your V2s, your N1s, your N2s, solve for what you don't have. So that's our N1 because it's 3.52 moles. That's going to be our V1 because that's volume, it's in liters, and we have our V2. So we're going to solve for N2. So now let's plug it into the equation. Volume goes on top, so we got 4 liters over 3.25 moles equals 5.5 liters over X. So you multiply 5.5 times 3.25. You divide that by 4. Do all that work, and it's going to give you, hang on, let me check my notes again to make sure I give you the right answer. It's going to give you 4.46. Uh-oh. So it's going to give you 4.46 moles. The rest of these are easy, so I'm only going to do one example on these. So all of these you should be able to solve by the examples we just did. So I'm just going to skip over all this part because I don't really have time to fit it into a big, long podcast. I want to keep this short, sweet, simple, to the point. So the combined gas law takes all 3 of those previous laws into account. Sorry, all 4 of those previous laws into account. So now we got P1 times V1 over T1 equals P2 V2 over T2. So if you're given 5 out of the 6, you should be able to figure out the 6th one. Well, for the very first one, you're going to have, okay, P1 is that, V1 is that, T1 is that. So you got 1.5 times our volume 1 of 30 over 20 degrees C. Well, let's go ahead and convert this C to Kelvin. So let's add 273, which is going to give us 293. That's going to equal, we have our P2 and our T2, so we're going to solve for V2. Okay? So we got 2.5 over 303. So you just simply cross multiply and divide again. So you got 1.5 times 30 times 303. Multiply this by that. We're going to divide that by 293 times 2.5. Now I haven't figured this one out yet, answer-wise, but if you just do that multiplication, that's going to give you your volume 2. Okay? The rest of these are going to work the exact same way. Again, it doesn't matter. As long as your pressures are the same unit, see how this is atmosphere and this is atmosphere, you don't have to convert it. Okay? If they're different, which none of these appear to be different, you don't have to worry about converting anything. That'll be it for right now. Next time we'll talk about Dalton's law of partial pressures. We'll talk about Graham's law of diffusion, and then we'll also cover the ideal gas law. But this will give you a good start on what to cover when you're dealing with gas laws. Hope this helped you a lot. This has been Coach Heichel. If you need anything, please feel free to email me. Thank you. Have a great day. Bye.